In this part of this video, I would like to discuss about the internal flow application. So I hope that you follow this part and get a hands-on experience using this internal flow with the case study of pitch daily study. So if you are able to recreate this case, then you can use it or utilize this template as your own case. For example, if you want to simulate a mixing flow inside a valve, let's say, or maybe calculating the velocity distribution and also the pressure drop inside a piping system, or maybe if you want to expand more, like design the pump system, or maybe manifold, everything that related to internal flow, maybe you can learn from this basic using this pitch daily study. So in this part, I would like to discuss about the use of the boundary condition specifically for the internal flow condition, and maybe some patch setting for the walls, maybe in the inlet, outlet, and entrainment, let's say. Then maybe in the like at the end of this course, you will learn how to use the snappy hex mesh to make a complex geometry. Then you can just like apply the complex geometry with the similar boundary conditions in this part. So that's why I make this simple case, so you can understand the basic idea of the boundary conditions for the internal flow. So we will copy the pitch daily study. Actually, we have lots of pitch daily cases in the tutorial folders, like pitch daily LES and maybe some experimental things, but the most basic set or the most basic to understand is the pitch daily study. So let's just copy first the pitch daily study. We can copy it from the Windows Explorer here. I mean, tutorials, then incompressible fluid and pitch daily. Yeah, we have lots of pitch daily here, like pulse, LTS, LES, etc. So we just copy this pitch daily study to our new folder. Let's say trial 4, let's say. It really doesn't matter what's the name of this, and paste here. And as usual, we will open the WSL to run the command line. Okay, maybe the thing that you must understand first is the structure of the block mesh of this pitch daily. So I hope you follow the previous section about the block mesh, so you can follow this easily. The only difference maybe here is just the non-parallel or non-perpendicular blocks for this hex 6 and I mean like these two blocks. So if you want to modify this, for example, if you want to increase the length of this blocks, you can just edit the x coordinates, or maybe if you want to delete this part of this part to make just a straight flow, you can just delete these two blocks, let's say, because sometimes some benchmark study just use these 3 parts of these blocks. So you understand how to remove them from the block mesh dictionary. And I think I don't have to explain everything here, because it's just like basically the same as the previous discussion. So let's just go to the folder within the project files, then the trial core and pitch daily steady. Then let's just create a block mesh, so we can check it on the power view by creating foam.foam, let's say. Touch foam.foam. Okay, then we can drag and drop this foam.foam to check the block mesh. And here we go, we see the block mesh with a beautiful grading like this. So you can see that nearby the wall you can see that there is like detailed mesh to capture the boundary layer. Then here you can see the like higher resolution mesh to capture the separation here. We will observe that later. And far away from the wall we can see that the mesh is bigger, so it will be more efficient. And for the grading itself we can see that we have two regular grading here and different grading here and here. So so the basic idea is just the same as our previous discussion about the block mesh, that the grading here must be the same as the grading here, and the x direction here must be the same as the x direction here. Let's just check our block mesh within the system folder and the block mesh. And let's just scroll down. This is the coordinates. And one interesting thing here that you must notice is that we use the parameters. So instead of just input it one by one, the grading here, we use these parameters, so we don't have like to if we want to edit something, let's say we want to edit the expansion ratio or maybe the location of the mesh, we just like edit here and automatically will be changed here. So you can use this idea by implementing the $sign here. So it is not only works for the grading, let's say you can also like for example the resolution, let's say you can make like resolution 1, let's say, then you can use the $sign here as the resolution, and of course with the value, let's say 18, but we won't do that. And the basic idea here is just the same as the grading with 3 parameters. So we have resolution here and we have the expansion ratios and the locations. This is just basically the same with the definition of the walls, etc, etc. Okay, that's it about the block mesh. I can show you here if you want to take a screenshot to understand the idea. So it is like a simple grading but using this parameter. So parameterization is quite useful if you want to use some, you don't have to change everything every time you make a small change. And here we go. The most our main discussion is about the boundary conditions. So for internal flow, we have to have the inlet, outlet, and also the walls surrounding the like the system. So it's called internal flow, as its name suggests. And in this case, or maybe in like a typical typical internal flow structure or internal flow cases, you will find that the inlet is input using the uniform velocity, or in OpenFOAM we also have a fixed value of volume flow rate or mass flow rate. And for the pressure in the inlet, we use the zero gradient. So zero gradient, it means that we are not specifying the fixed value. Let's say if we input like a pressure of 1 atmosphere, like a 10 to the power of 5 Pascal, let's say. But instead we use the zero gradient. It means that it has a certain value of pressure, but it will be like automatically calculated based on the flow. So we have certain amount of velocity, the number of pressure of the value of pressure will be calculated by, let's say, the pressure drop. So zero gradient means that it will follows the flow. But for the outlet, it is the opposite. You use the U as the zero gradient, so it will be like automatically calculated by the like flow pattern. Let's say if you have a high velocity here with small area, if the area is larger, it will be like a smaller velocity in the outlet. Or maybe if you have like a turbulent like unsteady flow, the velocity distribution here will not be constant, so we must input zero gradient. Let's say in this part of the outlet, like the top part will be high velocity, and the like the bottom part will be like the low velocity. It will be not constant. Actually, you can input the uniform value here also for the velocity, but it will be unstable if you are calculating using like from the numerical scheme. You will find a divergent because we know that intuitively from the physical like physical calculation, it will be the same mass flow rate, but from numerical standpoints, we do not always satisfy that condition. So the safest way to input is to use this zero gradient. And the opposite from the inlet, the pressure value here is the fixed value. Let's say a uniform 0. If we want just like calculate the delta pressure, it will be easier to use 0. Let's say we have from the result we get like 10 pressure, so we know the delta P or pressure drop is like 10 minus 0. But if you are simulating using, let's say, the ideal gas model, which the pressure become important, maybe you should specify the pressure, let's say like 1 atm or 1 to the power of 5 Pascal. And the other is just the turbulent parameters. Like the K is the turbulent kinetic energy, W is, or omega actually, is the specific dissipation rate, and the E is the dissipation rate, or epsilon I mean. It will be discussed later in the turbulent modeling. And for the walls, we use the no slip condition for the U, so it means that we specify the velocity 0 on the wall. Actually, we can also use like the uniform value of 0, 0, 0 instead of no slip, because like they are interchangeable actually. And for the wall, we can also input the velocity, let's say from the previous example, from the lead driven cavity, we use like the specified X velocity on the wall. So it also possible if you need to do that. And the pressure is zero gradient, means that it will be automatically calculated based on the flow. So it will like vary along the line, or vary along this flow. And the turbulent condition for the wall is the wall functions, which will be also defined later in the turbulent part. And these are some important notes that I said earlier, that if you use the specified inlet value, the pressure must be in the pressure on the outlet must be 0 gradient. And if you want to input the specified pressure condition in the inlet, the outlet velocity must be 0 gradient. So let's say you have a specific value for the pump that you want to set is as the input, let's say, or the if you have the pressure data instead of the flow, you can use this condition. But again, for the outlet, you must input the 0 gradient. Again, you can input actually same fixed value inlet and outlet, but it will be leads to a divergent instead. Except your simulation is like a very stable and very simple simulation. And no slip condition is basically the same as the velocity of 0. So yeah, they are just equivalent. And here in OpenFOAM we use the pressure is like a pressure divided by density. It is like the consequence of like numerical reduction or anything like it. So if you find the pressure in the paraview, it means that it is like a pressure divided by density. Okay, you must note this because it is not like a Pascal unit. So it is quite useful actually if you are simulating the water and air, so you don't have to worry about the density and you can convert it later. Then we can sometimes facing the entrainment or free boundary conditions like this. Let's say it is inlet condition and outlet for the suction, but you have like a free zone that there is inflow and also outflow in the same boundary. Sometimes it happen also for the outlet if we like to use the like a very large system, and the oscillating flow still occurs nearby the outlet. It will be sometimes become also entrainment. For simple case, we can actually just use the constant value for the outlet or the entrainment. So we can use like the P equal to 0 uniform like the previous example, but sometimes it's like to have a tendency to become oscillating if we use this if we use this constant pressure, because it is like for the outlet it will be no problem, but for the entrainment condition the pressure is actually just static pressure, so it does not include the velocity, so the energy will be lower inside for the inflow condition. Instead, it is recommended to use like the total pressure. Use this code, total pressure condition, which is the pressure that considering the effect of dynamic pressure, which is the half of u square, which is the velocity squared, then it will be more stable here. But again, for some simple like a simple case, you don't have to worry about this. It's just a simple note. Maybe one day you will need this if you are facing entrainment dominating problem. And for the turbulent modeling we will discuss later, but as a starting point you can use these values to estimate the input of the boundary conditions. So if we look at these files at the zero folder, we can see that the epsilon, k, and omega, we must specify some value. Let's say for the epsilon we can input that 14.8055 or anything like that, or maybe for the omega we also need to specify the uniform value. You can like estimate it from here, which the I is the turbulent intensity, can be determined. Let's say if you have like a like 5% turbulent intensity or 10% turbulent intensity, it's sometimes specified in your journal, let's say, for the reference. But if you don't have that value, we can use or estimate from the Reynolds number instead. So it is last the how to estimate this turbulent intensity. And the UREF is the reference value of velocity. So like the inlet velocity, let's say, and it is just for the internal flow, so it is not applied for the external flow. We will discuss later. And the epsilon also we can calculate it from this equation, with the L is the length scale, let's say the diameter of the inlet. And again, it is just like estimation, so it is just for the initial condition. So when the simulation begins or starting to like increasing the number of cycle, it will be not, the number will be diminished, so you don't have to worry much about that. But for some cases like turbulent K omega model, sometimes it is become unstable if you don't specify it like properly, so it will be critical for some turbulent models. Okay, but maybe we don't have to check a lot of here, just try to run this simulation. And maybe we want to check the nano for the zero folder and the velocity here. We can see that the inlet has the fixed value of velocity, and the outlet has zero gradient of velocity. And for the pressure, we also have zero gradient for the inlet, and outlet as fixed value, which is 0. So yeah, that's all. That again, we must follow this rule. Okay, maybe the other thing is just the same. Empty means just empty. It is like a two-dimensional. And okay, maybe that's all. And you must understand that this uniform condition is like we can use another value like a non-uniform value if we want like to define the inlet as the fully developed boundary layer, let's say, but it will be a rare case for this. And it is also important, the internal field is like the initial value of the whole system or the whole condition. So sometimes it is more conservative to just input it in the 0 value. For the external flow, let's say, internal field will be the same as the inlet. Let's say if we have an aircraft with the external flow like 10 meter per second, so we need to like easier to initiate the internal field with the 10 velocity also, like so it is like easy to start. But for the internal flow, we usually use this 0 internal fields. So before the flow started, the 10 meter per second is only occurs in the inlet, so it is much more stable compared to like you define everything like a 10. It will be like a problematic if you specify it like here. It will be like leads to a divergent. And okay, maybe just like just run the simulation. Foam run, I mean. Okay, let's pause it. And here we go, we got the convert solution. Converts, it means that it like satisfies the residual values which is stated in the system folder. And finite volume scheme, finite volume solution, we see here some like the residual control. So if they satisfy the value residual, it will be like a converts. Even if you are define the control dictionary as, let's say, 2000 iterations, it will be stopped if they are converts. So convergent condition is basically not not a natural like requirement, because you can edit it the residual, but the idea is that you can set the smaller value of the residual if you want to get a better solution. But sometimes it is like not that easy to find to get these values for some like transient or maybe complex simulation. And let's just touch this foam.foam again, and we reload our files, and here we go. We now have some time values. Okay, I think it is not a regular, but it is okay. You can get the value 289. It means that it is just the last iteration here, 287. And we can also check here. Sorry. Oops. That we have some values here and the convergent value 287. Okay, let's just make a slice here in the Z normal direction, and here we go. Our velocity distribution. Oh, sorry, I mean the pressure distribution. So for the outlet, it will be 0 value, and it will increase over there, over like the other direction of the flow, and maybe the velocity. Let's see. Here we go. We have a separation condition here, and the velocity is lower because like the after separation it become larger area, so smaller. And the outlet, the velocity will be not uniform, because in the inlet we see that it is like uniformly 10 meters per second, but for the outlet it is not uniform again. You have like higher velocity here and the smaller velocity here. That's how the zero gradient works. If you input not a zero gradient, maybe it will not like this distribution, and the result of course will be different. And nearby the wall we can observe the no slip condition, which is like a zero velocity here, if we see. And this is very crucial for the definition of the mesh, but we don't have quite a good mesh here to capture the boundary layer. But we don't have to worry much about this, because the like a wall function from the turbulent modeling covers this model. But again, that will be a tricky thing that we must to discuss later in the turbulent modeling.